I must first of all apologize that I lost my voice during the day. And nevertheless, I think you can hear me. I will. We heard an extremely important and sad message, and it's influenced by this in the spirit that I want nevertheless to say. For me, always the definition of happiness has been the capacity to be curious. If you lose curiosity, you become a vegetable. So that all those in science, for example, I always wish them curiosity, perseverance, and optimism. Now, what about evolution? Not at the level of a whole organism, but at the level of a unique discipline. I would like to discuss here the science of immunity, the immunology that is responsible for fighting diseases by vaccination, to cure autoimmunity, for fighting cancer, and so many other areas of everyday life. But immunity, as we understand it, starts only in the case of fish. It was more recently discovered the more primitive animals here, nevertheless, have some form of immunity which is now defined as innate immunity, as contrasted with what we always called immunity and now is called adaptive immunity. But even those of us, those above fish, let's say, including the humans, that possess the capacity of adaptive immunity, it appears that this adaptive immunity was dependent upon a functioning innate immune system, even in us. Among the early discoverers of innate immunity, which is the last 10 or 20 years, I would like to mention Charlie Janeway Jr., Jules Hoffman, and Ruslan Medjidov. Apparently, the innate immune system is as old as the emergence of multicellular organisms from the primordial slime. In this lecture, I shall give example, one in the area of autoimmunity around an antigen, the other an area of cancer, making use of antibodies. Already there. Okay, until close to the end of the 20th century, the idea of treating autoimmune diseases or cancer with antibodies or antigens was almost inconceivable. Usually the drugs were small molecules. Insulin was a rare example of a protein being used as a drug. This has changed in recent years, with several proteins, including diverse antibodies being used in medicine. Now, one little bit of chemistry. To make a polymer composed of amino acids, amino acids are the building stones of proteins. But if you want to make models of proteins, you have to use technique. Actually, what I'm showing here is you need phosgene to develop derivatives from which you can make polymers. Now, why are we making polymers of amino acids? Because we want them as models for proteins. And in many cases, we were successful showing that you can make a synthetic polymer that resembles collagen, and at immunological level, they will cross-react. The same are enzymes like lysozyme. So with this, we start, and I'll come back to earlier work, but I'm leading to the drug against multiple sclerosis called Copaxone, which is the first example of a polymer of amino acid uses the drug. But historical, I don't even know. No, this is probably only for me, because when we had a material, a molecule, which was not antigenic at all, gelatin, and you convert it by attaching chains of amino acid tyrosine, and it becomes antigenic. And then, if you attach a little bit of tyrosine, you get antibodies against gelatin. But if you attach more tyrosine, it becomes also a very good antigen, but makes antibodies against chains of tyrosine. So this led me, and this was the first time that I introduced, probably almost 6 years ago, the notion of immunogen and immunogenicity, to distinguish between the capacity to make an immune response and the reaction, the antigenic specificity. And then we prepared a synthetic antigen, which was a multi-chain polymer, and the various colors stand for amino acid. It's a chain of polylysine, and on every lysine, which is an amino group, you can grow other chains. And so we had this antigen which has, at the end, has the yellow stands for a polymer of alanine, and then you have some other. I will jump immediately to one of the most important observations which made in the early 60s. Having very simple antigens and having inbred mice, which were very simple genetically. So antigens simple chemically, mice simple genetically. We could show that if we have at the end of the side chain tyrosine, one chain becomes a very good antibody maker, the other makes next to nothing. If we replace tyrosine to histidine, the reverse is true. If we replace it with another amino acid, phenylalanine, both became antigens. This was the beginning and the original discovery of the genetic control of immune response. Also, I would like to say that having simple antigens chemically, we could change them, the size, the shape, the composition. We could learn much about the molecular basis of immunology as of 50 and 40 years ago. Mice respond to a given antigen determined according to a simple Mendelian dominant pattern. This antigen is of a restricted antigenic specificity, enables to sort out antibodies against a relatively well-defined antigenic site. The genetic control of the immune response is specific to the antigen determinant. Now, if we inject bovine serum albumin, that has so many separate responses that you can't find any difference. And this brings me to another fact which I want to mention here, which is from an earlier period when I spent a couple of years with Chris Anfinsen, who was a member of this academy, and we showed that opening the disulfide bridges of an enzyme ribonuclease, we can leave it alone overnight and we get back all the enzymatic activity, which meant that you do not need any additional genetic information to tell an open polypeptidic chain how to get the unique architecture of a protein. In the same spirit, we wanted to study an antibody. But if you try to open all the bridges, all the disulfide bridges of an antibody, just drops out of solution. Then we used, with our experience with polymers of amino acid, that while poly-L-alanine is an utterly insoluble alpha helix, poly-D-alanine is an utterly insoluble alpha helix. But if you make polymer of D and L-alanine, it became not only water soluble, but it becomes a great solubilizer. So we could make a polydiol alanine antibody, open all the disulfide bridges, and by refolding, we recover all the antibody activity, which, by the way, was another confirmation of the clonal selection theory of antibody formation, that even an antibody left alone in its separate chains brings back the original antibody specificity. Yeah, no, this is the same saying that this was a selectionist proof. Now, I'm coming back to multiple sclerosis. This, the idea was that in the brain there is a positively charged protein called myelin basic protein. And if you inject it in experimental animals, it produces a disease which might be a model for multiple sclerosis. So what we did, we prepared a polymeric model of amino acids, much simpler but trying to resemble myelin basic protein, and we tried unsuccessfully several polymeric models to inject into experimental animals and to get them sick. It took us 1.5 years until we realized if it cannot make sick, this was the drug which ended up healing multiple sclerosis. So again, when people ask me, I said I never wanted to heal anybody. I wanted to have a good model. This brings me to the general notion to which I'll come back, that I'm a great believer in basic research, in curiosity-driven research. At least in my case, the best results, which became very practical, came from the basic research. So, this has been so much used. I'll just repeat what's written here. It suppresses the disease, the experimental disease in mice, with a complicated name of experimental allergic encephalomyelitis. It's not toxic, not encephalogenic. It's not a general immunosuppressor. We learned early that we did more than we expected, because the polymer which we prepared, which became the drug, cross-reacts immunologically with the natural myelin basic protein. But if we replace L-tyrosine with D-tyrosine, which doesn't cross immunologically and also doesn't help, here I'm showing in different species, including rhesus monkeys and baboons, and I'm proud to say it because we made rhesus monkeys sick, and we healed them, all of them, with the material. And this was essentially it convinced everybody that this was working. You must remember, this is the first time a macromolecule, even worse than protein, because protein is a big molecule, but at least every molecule is identical with another. Here, everything is wrong. No two molecules are similar. They're all around something, but it's all statistical. I'm showing here the first studies published already in 1987 in New England Journal of Medicine. And I always insist how important it is to have a statistician next to you from the beginning. But you don't need a statistician to see that the upper half has more black points than the lower. Every point is an attack. And you see that in those treated, there are many fewer attacks. Then slowly, it still was terribly difficult, and we had never an experience. I'm jumping because there are probably at least 100 papers and many studies all over the world. I will just tell you without going to the details, that we have now proved that this copolymer which we called COP1, COP1, COP2, and in industry they put AX, so it's Copaxone, because it's immunological and neurological disease. And we know that Copaxone not only decreases the rate at which there is remyelination of the nerves, but even we could show that, of course, not in human, but in the experimental model of disease, that it can only slowly remyelinate. So we have some proof. This is also by using techniques in the magnetic resonance. You see the difference in placebo and red, and the other name is glatiramer acetate. It's a bad name, but I won't go into the details. And this shows the first 12 years that the number, this is always the exacerbating, remitting type of multiple sclerosis, and you see that it stays over the years. At this stage, there are close to 300,000 patients in 50 different countries who are receiving it, and a great majority stops having these attacks. But science being science, I will be very disappointed if sometime soon we won't have a better drug. And there are quite a few candidates, but you need both greater efficiency, but also to be sure that you don't have some bad cases. And this lets me move to the other topic I want to discuss in the case of antibodies. I'm terribly sorry, I don't know whether even are not able to hear me, but this is not my usual voice. It's terrible. At the beginning, we started, this is so early that there were no monoclonal antibodies. 50 years ago, I had the idea that if I can take a chemotherapeutic small drug against cancer and attach it with a light covalent bond to an antibody, which was still a polyclonal antibody, we may have some improvement. And we worked for quite some time, we published quite a lot, until one day we discovered, this is just showing the red is always the best result when you have the conjugate, and the others are all the controls. But then we discovered some 20 years ago that in the case of an antibody, by now monoclonal antibody, against epidermal it's a series of tyrosine kinases which are used a lot. And we found out that even without binding, just by giving at the same time the antibody and the drug, cisplatin, we got this red line which prevented totally the disease. And again, you learn from experience, and we didn't, as a president of the Weizmann, I was preaching to others that if something is interested, you should patent it, you should take care. But as a scientist, I never did it. So it ended up that somebody stole and made a patent, and we had to go to the federal court in Manhattan. It was all returned to me. And now I have the best proof, because this is the second blockbuster which brings the Weizmann Institute quite a bit of money. And as I'll show you in a moment, and I'll tell you now, Some of you may remember there was a great American lady, Gertrude Stein, sitting in the 20s in Paris, and she had the famous expression, a rose is a rose is a rose. And I used to say at lecture, a monoclonal is not a monoclonal, it's not a monoclonal. And you see in a moment the difference, but I see that I put something. Yeah, well, these are the RB receptors as targets. I don't even need it. I want to make it as simple. I have pity on all of you, but I want to show you the yellow on the right shows that the first column, which is a control, but then the last but one column shows that there are some molecular antibodies which speed up the growth of the cancer, of tumor. Some are almost irrelevant, and those which are almost non-existent are the good antibodies. So this is just to prove what I showed you a moment ago. So in a general way, combine, because all this has to do with synergies. The first example I give you is the fantastic synergism of an antibody and a small molecule drug for cancer. And usually there are discussions who was first, but in this case, the various companies that come to ask for right to use the patent prove that in this case we were the first. Now, I won't go into this hour. We use the expression epidermal growth factor receptor is the first one, and now it's renamed RB1. There is RB2, 3, 4. They are all binding to a receptor. Some are missing a receptor. Some are missing the other quantities, but the combinations are very good. And I want, obviously, this can happen, the synergistic effect of two antibodies. This was the next one, and I'm ashamed to say that we were so happy to publish in PNAS the paper, and then I get a request for a picture, and the American Society for Biochemistry and Molecular Biology, they are publishing something, so they wrote an article, two are better than one. And this reminded us, of course, we couldn't patent anywhere but in the United States. But again, the pleasure of publishing is in the end, for a scientist, more important than any additional fact. But what I'm showing here is just, if you look on the upper two, where there is a very good effect with the, with the sign, it's because you have to have different antibodies against different epitopes of a receptor. If they are against the same, there won't be such an effect. It's only in those cases, which is the blue in the upper, that you have this effect. And I won't go into detail, but combination of anti-receptor antibodies help very well. And we see the explanation is a combination of these anti-receptor monoclonal antibodies against distinct epitopes crossing the receptor. And now I move in the last few slides what preoccupies me in the last few years, and this is pancreatic cancer. Pancreatic cancer is one of the worst ones because it's very quick. You have just examples. But what we are showing, this is a homocombination, two antibodies against different epitope of the epidermal growth factor receptor, also called RB1. And the picture on the left shows the size of the tumor, which the first one is the control and the other is smaller. The second to the right shows how many mice are without tumors. And again, if you have the right combination, the blue showed that most of the mice were without tumors. And I'm not giving you the detail of these last additional studies, but this is a case of hetero-combination, when you have one antibody against EGFR or RB1 and one against RB2, and this is the best one, the one at the bottom. It's not a simple situation, because after we have all the data, most humans that die so tragically die because in most of them there is a genetic marker called KRAS. And now we are in the middle of investigation showing that we have a way in which we can activate also the KRAS. And even then, probably within a year, you know, I'm talking, I have a lot of, as I told you, perseverance and optimism because I'm over 90, and this will take at least 1 year, and then we have to humanize. So it's another great investment of many millions of dollars, but it's so cruel and so on, so I'm going full steam, and if I'm still around in 3 or 4 years, I'll be happy to talk here about showing that we can treat humans. On the one hand, I have 2 cases in which I helped, but on the other hand, it's almost impossible at the third time it would be also so successful. So I want now to finish, you know, almost 40 years ago, when I started, I was appointed, this was Pope Paul VI, and I was responsible for a study week on the role of non-specific immunity for the cure and prevention of cancer. And then, let me, and then I would like to quote here the last words of my concluding remarks of almost 40 years ago, because I said it then, we must remember well one thing. We are dealing here with matters of paramount importance, and under no circumstances should our devotion and our enthusiasm run ahead of our carefully checked and statistically evaluated data. Immunology, as I deeply believed, I said this 40 years ago, a lot to contribute to the cure and prevention of cancer. Let us take a more cautious but beneficial road, which may be slower, but ultimately led us to significant progress and lasting achievement. Now, as you are aware, the journal Science said this year that the greatest result, the greatest, it's wrong to say discovery, the greatest achievement last year was the use of immunotherapy in cancer, the same in Time magazine. So it's now an important role, and especially the new, it's new now, but it was born by a colleague in my laboratory, Zelig Eschar, who is now mentioned everywhere, because he took, you know, you have 2 arms. You have antibody, you have so-called T cells. Now, T cells are terribly important, but they're not so specific. So somebody, I mean, the Zelig Eschar took the genetically the part which is responsible for specificity and put it on the T cells. So now you have T cells which are as specific as antigen. And he worked on it, but he didn't lead it. Now other groups in America took it to the clinic, and this is a great excitement now. So I'm happy that with enough perseverance and enough optimism, it is the case when this is becoming now of paramount importance in cancer treatment. That's all I have to say.